Okay, so the final magnitude that we're going to talk about here is something called absolute magnitude. That's the big M. Okay, big M is the intrinsic magnitude of the star. Okay, it is defined as is defined as what its apparent magnitude would be if you were 10 parsecs from it. Okay, so the problem is that when you look at stars, you don't know whether a bright star is bright because it's close to you or whether a bright star is bright because it's really bright. Okay, so what a absolute magnitude does is it compares all the stars on a distance neutral background, right? So stars that have a large or a small in this case, right? I don't know. But stars that are bright, absolutely bright, are really are bright. It's not that they're close to us, it's that they really are brighter stars than other stars that have a dimmer absolute magnitude. Okay? It's so hard to talk about because this is the same reverse scale, right? Where negative numbers are super bright and large positive numbers are super dim, right? But things that if it is bright by absolute magnitude, it really is bright. Now, the way that you correct for that is this formula right here. And this guy's in your data packet. But the one for M, mysteriously is not in your data packet. Okay? Now, if you look at this thing, it's like G, it should involve the distance to the star, right? But it should be squared. Well, do you remember that there was like a 2.5 out here? Well, the 2 came out that was the square because of logarithms. I don't know. You can show it. I'm not going to show it, but you can actually derive using the formula for apparent brightness and for apparent magnitude. You can derive this one, okay? But I'm not gonna. Anyway, so let me just do an example, 2 examples here. Then you can decide what you want to do. So here's an example. Let's suppose we're 100 parsecs from a star that has an apparent magnitude of 6, right? What is its absolute magnitude, right? Okay, well, we can just go ahead and plug the numbers in here, right? If we go M minus big M, right, equals 5 log, I'm just going to not say base 10, okay, D over 10. Okay, if we want to solve that for big M, I guess we'll have to say M minus log 5 log D over 10 is equal to, is that equal to big M? I think so, because I added this to both sides, subtracted this from both sides, right? So let's go ahead and just plug the numbers in, right? So 6 minus 5 log, and then it's 100 parsecs, right? Okay, divided by 10 parsecs, right? And of course, 100 divided by 10 is 10, and the log of 10 is 1. And 6 minus 1 or times 5 is 1, right? So our absolute magnitude is 1. Now, if you remember this, in our previous example when we're talking about apparent magnitude, remember that the difference in brightness in the actual physics watts per square meter between a 6, which is very dim, you can barely see it, to a 1, which is a normal bright star, is 100 times the brightness. This guy's 100 times brighter than this guy, right? So how is that? How is it just 100 times brighter? Well, look at it. Remember that big M should be for when you are 10 parsecs from a star. But we're really 100 times. We're 10 times farther, right? So it's 100 times less watts per square meter, right? And so therefore it's 5 more in magnitude, right? It's dimmer. Remember the 6s, the big numbers are dim, okay? So that's the thing, right? You're 10 times closer. You have 100 times the light, so it's down 5 for the apparent magnitude, right? To make it into absolute magnitude. Or another way to think about it is that we're too far from the star for it to be fair, so we get ourselves closer, which makes the magnitude brighter. Okay, so let's go ahead and take a look at this. The sun has an apparent magnitude of minus 26.8. We are that many kilometers, or 4.9 times 10 to the minus 6 parsecs. So parsec's really big, right? Parsec is actually 3.26 times as far as light travels in a year, right? So we are like 8 light minutes or something from the sun, right? So that's why that's so small. So what is the sun's absolute magnitude, right? Its apparent magnitude is gigantor. It's a super large negative number, right? Which makes it really bright. So let's, what is it? It's m minus m equals 5 log d. Boy, I sure hope that's the right formula, you know? Okay, so how do we do that? I think we do. I think we want to solve for big M, right? Okay, so it's the same thing we just did. M minus 5 log equals big M, right? So minus 26.8. Oops, sorry. Minus 5. That's supposed to be a minus. Ignore that. That's like a little thing that holds up the minus. Log. And then our distance is 4.9 times 10 to the minus 6th parsecs, right? Divided by 10 parsecs. Right, and that's going to be our big M. So minus 26.8 minus 5 times log parentheses 4.9e minus 6 divided by 10. That'll be a good number. I get 4.749 or something like that, right? So M is 4.7, which makes our star. If we were 10 parsecs from it, would make our star not a super bright star, but you would be able to see it. We can see all the way down to a 6, right? So it wouldn't be a super bright star, but it's not wouldn't be the dimmest star we could see. And by the way, 10 parsecs is just sort of how far we are from a lot of stars, so we just picked that. About 32.6 light years. I'm going to do more examples. You don't have to watch. You can go on to the next video if you want. Okay, so let's see. You're 320 parsecs from a star with an absolute magnitude of 6.3. What is its apparent magnitude? Okay, let's see, apparent magnitude. So M minus big M okay. This is the same thing, isn't it, right? So M minus 5 log. Oh, it's apparent magnitude. We're solving for little m, right? So little m is equal to 5 log. That's a D. You know, what is it? Or we add m to it, big M. Is that right? Yeah, that's right, because I'm just going to add that to that side. So 5 log, and then our distance is, we really are 320, but we should be 10. Okay, so let's see, plus big M, and that's going to be our, let's see, I suppose that's going to be a positive number, and then, yeah, okay, I think we're good. It's going to be pretty faint, right? So 5 log, I'm going to live on the wild side here, not say times log. Okay, log of 320 divided by 10 plus 6.3. I get 13.825. 826 or something like that. But we only have 2 sig figs, so it's a magnitude 14. Very faint. You need a telescope for that. And that's why, of course, telescopes are big, because you need a big aperture to capture the light from such a faint star. All right.